acceleration. It is common that velocity changes. We can watch the cars on the road. Their velocities change more often than not. Acceleration is a measure of how velocity uh, changes with time. We know that there is average velocity, and we know that velocity is a vector, and we use this symbol to represent average velocity. And there is average velocity, and there is also average acceleration. And we use this symbol to represent average acceleration. And acceleration is also a vector. It has magnitude and it has direction. And we know that average velocity, the formula for average velocity is the average velocity equals the displacement divided by the time interval for the displacement. And similarly, the average acceleration equals the change of the velocity divided by the time interval for this change. And we know that there is instantaneous velocity, and we use this symbol to represent instantaneous velocity. And we also know that because the instantaneous velocity is much more useful than the average velocity, so normally if we do not specify when we talk about velocity, we are talking about instantaneous velocity. Similarly, there is also instantaneous acceleration. And we use this symbol to represent instantaneous acceleration. And also, because instantaneous acceleration is much more useful than average acceleration, so if we do not specify when we talk about acceleration, we are just talking about instantaneous acceleration. Now let's watch this position time graph. This is a position time graph. And we know that if the position time graph is a straight line, its velocity is a constant. For example, in this position time graph, from 0 second to 0.2 second, the position time graph is a line segment. So from 0 second to 0.2 second, the velocity of this object is a constant. And similarly, the position time graph from 0.2 second to 0.8 second is a line segment. And the velocity of this object from 0.2 second to 0.8 second is also a constant. And now, if this is a velocity time graph, so it means here it's not the position. Here it is the velocity, and um, its unit is meter per second. Direction is. If this is a velocity time graph, if the velocity time graph is a straight line, the acceleration for the straight line part is a constant. For example, from 0 second to 0.2 second, the velocity time graph is a line segment. Then the acceleration for this time interval from 0 second to 0.2 second is a constant. Similarly, from 0.2 second to 0.8 second, the velocity time graph is a line segment. Then the acceleration for the time interval from 0.2 second to 0.8 second is a constant. So from here, we know that the relationship between the velocity and the position is similar to the relationship between acceleration and velocity. Question. Figure 10 shows a graph of the motion of a car along a straight road. So this is a velocity time graph. And A. How can you tell from the graph that the car has a constant acceleration? B. Describe the motion of the car. C. Determine the acceleration of the car. So now question A. How can you tell from the graph that the car has a constant acceleration? The acceleration is the slope of the velocity time graph. And here, the velocity time graph is a straight line. If the velocity time graph is a straight line, then the object has a constant acceleration. B. Describe the motion of the car. So the motion of a car is that at the beginning, the car just stops there. The car does not move. Then the car accelerates with a constant acceleration to go to the north along a straight road. Now question C. Determine the acceleration of the car. So the acceleration equals the change of the velocity divided by the time interval for the change. And this equals. So at 6 seconds, its velocity is 12 meters per second. The direction is north. Then at 0 second, its velocity is 0 meters per second. And this is divided by the time interval for the change. So the time interval for the change is 6 seconds. And this equals 2.0 meter per second square. The direction is north. The standard unit for the acceleration is meters per second square and followed by the direction. Question. Examine the velocity time graph in figure 11. So this is a velocity time graph. And A. Determine the average acceleration for the entire trip. B. Determine the instantaneous acceleration at 3 seconds and at 5 seconds. C. Draw a reasonable acceleration time graph of the motion. Now A. The average acceleration equals the change of the velocity and divided by the time interval for the change. So this equals at 6 seconds, its velocity is around 36 meter per second forward. And minus at 0 second, its velocity is 0, so 0 meter per second. And the time interval is 6 seconds. 6 seconds. So this equals 6 meter per second square forward. So this is the average acceleration for the entire trip. Then B. The instantaneous acceleration at a time is just the slope of the velocity time graph at the time point. And here, 3 seconds is around here. And we draw the tangent line of the graph at 3 seconds. It's just like this. And the slope of this line is here. It's around 25. So it's 25 meter per second forward. At here, it's the velocity is 0, so minus 0 meter per second. And over, let's check this time interval. It's around 4.2 seconds, and this equals 5.95 meter per second square forward. So at 3 seconds, the instantaneous acceleration is just equals to 5.95 meter per second square forward. And now check 5 seconds. So 5 seconds is around here. And we draw a tangent line at 5 seconds of the velocity time graph. It's just like this. And the slope of this line is here. It's around 34. It's 34 meter per second forward. And here, the velocity is 0, minus 0 meter per second, and divided by the time interval. So let's check this here. The time interval here it's around 3.3 seconds, and this equals about 10 meter per second square forward. So at 5 seconds, the instantaneous acceleration is just around equals 10 meter per second square forward. Now C. Draw a reasonable acceleration time graph of the motion. The vertical axis is the acceleration. Its unit is meters per second square forward. And the horizontal axis is the time. Its unit is second. And here is 2 seconds, 4 seconds, 6 seconds. And here is 5 meter per second square forward. Here is 10 meter per second square forward. And here is 15. So from the graph of the velocity time, one time is 0, here is 0, 2, 4, 6. One time is 0. The slope of the graph at 0 second is also 0. So at 0, at time 0, its acceleration is also 0. And we also know that at 3 seconds, its acceleration is 6. It's about here. And at 5 seconds, its acceleration is 10. It's about here. Now we can connect these points with a smooth line to get the acceleration time graph of the motion. And this graph is like a straight line. It's because the graph of the velocity time is like a parabola. And we know that the slope function of a parabola is a straight line. So for the acceleration time graph to be a straight line, it's reasonable. Question: examine the velocity time graph in figure 12. So this is a velocity time graph. And A, determine the average acceleration for the entire trip. B, determine the instantaneous acceleration at 2 seconds, 4 seconds, and 6 seconds. C, draw a reasonable acceleration time graph of the motion. A, the average acceleration equals the change of velocity divided by the time interval for the change, and this equals, so at the end the velocity is 0, so it's 0 meter per second, minus at the beginning the velocity is around 49 meter per second forward. And over the time interval is 7 seconds. And this equals -7 meter per second square forward. Then this equals +7 meter per second square backward. So we know that the negative sign means that its actual direction is opposite to the direction at the end. So negative forward is positive backward. Then question B, determine the instantaneous acceleration. We know that the instantaneous acceleration equals to the slope of the velocity time graph at the time point. So at 2 seconds, 2 seconds is around here. Here, the slope of the graph equals to the slope of its tangent line at this point. So we draw the tangent line. It's just like this. Then we can find the slope of the tangent line. At the end, it's around 30 meters per second forward. And at the beginning, it's minus. At the beginning, it's 50 meter per second forward, minus 50 meter per second forward. Time interval is from 5 seconds minus 1 second. Then this equals negative 5 meter per second square forward. And equals positive 5 meter per second square backward. So this is for at 2 seconds. Then at 4 seconds, 4 seconds is around here. And we draw the tangent line of the graph at 4 seconds. It's just like this. It's just like this. Now we find the slope of this line. Here is 10. Here is 50. So 10 meter per second forward minus 50 meter per second forward. And the time interval is here 7. Here is around 1.5 with 7 seconds minus 1.5 seconds. And this equals negative 7 meter per second forward. And equals positive 7 meter per second square backward. So this is at 4 seconds. Here it's the instantaneous acceleration. Here, instantaneous acceleration. Similarly, we can find the instantaneous acceleration at 6 seconds. And now question 3, it asks us to draw a reasonable acceleration time graph of the motion. So see, I draw the graph here. So the vertical axis is just the acceleration. And its unit is meter per second square. Here is backward. And the horizontal axis is the time. Its unit is second. And here is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Then Now here is 5. Here is 10. Here is 15. Now here is 0. So from the velocity time graph, we can find that at the beginning, at the 0 second, the slope of the graph is 0. So at time 0, the acceleration is also 0. So at 0 second, the acceleration is 0. Now at 2 seconds, its acceleration is around 4 meters per second. 4 meters per second square. So at 2, it's 4. It's around here. And at 4 seconds, its acceleration is around 7 meters per second square. So it's around here. And at 6, it's around 12. It's around here. And then we use a smooth line to connect these points. And we found that the acceleration time graph is like a straight line. That's because the velocity time graph is like a parabola. And we know that the slope of a parabola is a straight line. So it is reasonable that the acceleration time graph is like a straight line.